So now we are going to look at Kepler's laws of planetary motion. We'll just call them Kepler's laws. Kepler's three laws. Okay. Huh?
Why 3?
Why not? Kepler's three laws. So Kepler, when he was looking at maybe, well, I'll do it in yellow. Here's your sun.
Oh, it was the ellipse thing, is it?
Yes. All right. Give me my. I can't see my yellow. There it is.
Yeah, nobody can see the yellow. So can you change it?
Now you can see there. All right. And then we'll do green for Earth.
No, blue. Okay.
Well, actually, you're right. It should be blue, not green. No, you're right. It should be blue. It's more blue than it is green. All right. Now, Kepler noticed something when he looked at planets orbiting suns, or well, in this case, planets orbiting their sun. He noticed that the path is always elliptical,
What's elliptical?
which I think,
You spelled it wrong.
I know I did. Did they say, hang on, let me check your worksheet. Hmm?
Just E double L and then
E double L, I P I C A L.
Elliptical.
Elliptical.
PTICA.
P T.
Yeah.
I left out the P.
PTICA.
Are you sure double L?
Yeah, it's written
Well, I didn't get the second paper.
on the
Okay, no, I believe you. I'm just wondering if there's like an American spelling or something that makes it different. It's just a double, alright, no double L. Alright, double L. Fine. Okay, so you have elliptical. And do we know what the word elliptical means?
Yeah.
You don't know? Yes? You know, how do you explain elliptical?
It's the shape. You know the shape ellipse.
Yeah.
No, if they don't know elliptical, why would they know ellipse?
Maybe they know ellipse, but they don't know elliptical.
Just like egg,
Huh?
the shape of egg.
Very good. It's like the shape of an egg. You know an egg?
Oh, okay.
You understand?
Okay.
Same shape as this. Now, what's so special about this shape? Well, let me show you what's special about this shape. If you have something elliptical,
Okay.
there's two special points in the center. And what's really special about these points is that if you imagine you have like a laser, you know a laser? Like a light. So you shoot a little light out here. And imagine this here is a mirror.
So we'll come down to the earth.
It'll bounce not back to the earth,
Oh,
but
Yeah,
back to
it's
this
there.
point.
I know.
So the point is, no matter what way you shoot out here, and if you were to bounce off this path, you'd always bounce back to the other place. So if I start here and go like this,
We'll go back to the point.
go back to this one. Or if I start here,
Go back to the
it always happens. So there's two places here. And these two special points, okay, foci, focus for one, I believe, or that easily could be the other way around. Foci, focus. One is singular and one is plural. Yes.
If we regard the red light as the light,
Yes.
that means the light, once the light changes the direction, it will cause the point.
Yeah, like what happens, yeah. If you look here, imagine I send light out here, okay?
Yeah,
And then I put a mirror. Do you know a mirror?
yeah.
Here. The light will come along, hit the mirror, and will always go back to this point. Now, it might be a little easier if I draw you this one here. Imagine this is a table, okay? And on the, you all know snooker, don't you? Do you know snooker?
Yeah.
Oh yeah.
Now, imagine this is a snooker table, but instead of being a rectangle, it is elliptical. If I have my ball here, and I hit the ball, it will go this way,
And come
it'll
back
hit off this,
to the hole.
and it will always go
To the hole.
to this, past this place here.
Like Polly.
Huh?
Polly.
Like pulley?
So does
Pole.
this.
Huh?
Polly.
What's this? Pool?
Pole.
Pooling? What's
Yeah.
pooling?
Polly.
One six snooker.
Oh, that's pool.
Yeah, pool.
Just pool. Yeah. So if you hit it here, it will bounce and always go here. Or like if you hit, like say if I hit it like this, it'll go here, it will bounce and go back here. So anyways, what Kepler noticed is that the sun is always at this point here. So for example, let's say I have something like this, and I have my sun here, and I have my earth here. I know that the sun will always be at this focus, will always be there. And this is Kepler's first law. Kepler's first law says that the orbit is elliptical. That's Kepler's first law. So first law, the orbit is elliptical. Whoops. Yes. Oh. Please try not to die. Please.
So in the exam, for example, they asked what is Kepler's
They
first
could,
law.
yeah, they could, yeah.
We just say orbit is elliptical is fine. Or
You could say the orbit is elliptical, and the bigger mass, in this case like the sun, the bigger mass is at a focus point. That's Kepler's first law.
I've tried this one.
Yeah, this is his first law. Okay. Number 2.
Can I see it? Because
Yeah. Second law.
small mass gets.
No. Let's say the planet starts here at t equals 0. Okay? And then maybe here is t. Actually, let me draw it a bit better. Let me make it more extreme. Okay, and here's the sun. So this could be a planet very far away. Okay, so let me just color this in. So I'll call this piece here red, and then this one here green. So the red one is area 1, and then the green one is area 2. So let's just imagine, for example, it takes the planet 1 day to do this. And then it takes another 1 day to do this.
4 by.
No. Just for a moment, it takes 1 day to go from here to here,
Okay.
and then 1 day to go from here to here.
Okay.
What Kepler noticed is the area in each piece is always the same.
They are the same side.
Same area. So area 1 will equal area 2 if time 1 equals time 2. So if this is a day and this is a day, well then this area will equal this area.
T equal T.
T1
T1
equals
equals
T2, yeah.
The time?
Time.
Okay.
So how do you say this in a phrase?
How do you phrase this exactly? Yes. You could say that the rate of change of the area is constant.
The rate of the area change.
The rate of change of area is constant. In other words, the area made in one day is equal to the area made in the second day, which equals the area made in the third day. The area is the same each day.
What's constant? What is road?
The rate,
Yeah.
or ATE.
What's that mean?
Rate means how quick it changes. Okay, are you happy with that? Yeah. And then law number 3. Law number 3 says,
There's no formula?
this is the one, law number 3. T squared, that's the time to do one orbit, is equal to 4 pi squared over gm times d cubed. And I'll explain what each one is. That's the time to orbit once, and this here is the average distance to m. So I'll draw you a graph to explain this. Just tell me when you're ready.
What do you mean by average?
Yeah, I'll draw a graph to explain this now.
M is the origin, like the sun.
The bigger mass. For me, big M is bigger mass and small m is smaller
It
mass.
must be the origin.
Yeah, well, always the bigger mass, which should be at the origin, yes?
Times D cube.
Yeah.
And in G is the same value as
Oh, yeah.
6 point.
Yeah, yeah. Okay, can I draw a graph now?
Yeah.
Okay. So let's go. I'll explain Kepler's third law now. So you have your, let's go with our Earth again. Earth, Sun. Now, if you look at his formula, what he's saying is that the time will equal square root 4 pi squared over gm d cubed. Basically, that's his formula. Kepler has given you a formula to calculate the time to go around once. Okay? Do we know, let's look at what we know each here. Do we know the G?
Yeah.
Yeah, we know the G.
And there's
6.67.
Mm.
Do we know the M?
Yeah.
Which is it?
M to the F.
No, for the Sun.
Why?
It's the bigger M.
Okay.
And do we know 4 pi squared?
Yeah, 1 day.
Yeah, 4 pi squared we know.
Okay.
So the only thing we are not clear on the meaning of is this here.
The D and
D.
the T.
The d cubed. The t is the time for one orbit.
Okay.
So what does this d cubed mean? Well, what d cubed means, if I look here, let me call that distance d1, for example. And then tomorrow, maybe it's here, I call this distance d2. And then the next day, d3.
You plus all of them and divide
Yeah,
by
exactly.
100?
Yes. Well, it depends how many days I take. If I do a year, it'd be 365.
Okay.
So basically, the D is the average distance from the Sun. Maybe as an example, let's work out what the D is. Okay? So let's do Sun and Earth. Alright? What did we say the mass of the Sun was? It was something. It's in one of your questions. What is it, like 10 to the 11 or something? Is it, or
10 to 30, I remember.
10 to the 30? Was it? What was? Yeah, so m equals, let me write the formula in. 2 times 10 to the 30, yes? And the g is 6.67 times 10 to the minus 11.
Yeah.
All right? And then you have 4 times pi squared with the d cubed. And the t, that's how many seconds there are in 1 year, which is something like roughly, I think, like 31 times 10 to the 6 seconds. Something like this. Or 3.1 times 10 to the 7.
This is the time?
The time, yeah.
How did you get it?
How did I get this?
Yeah.
It was 365 times 24 times 60 times 60.
Oh.
This is the 1 day, right?
1 year.
1 year.
So, Hussein, I would like you to calculate, let me highlight which part I want you to calculate. Calculate that part, please.
Without the d squared?
Without the square root and without the d cubed, yeah.
It's 5.44 multiplied by 10 power
5.44 multiply
by 10
Radian or
power
Radian or degree?
doesn't matter here.
minus 10.
Minus 10
Yeah.
d cubed.
Yeah.
And there's a square root here, yes?
No, I eliminated this.
I told you to.
No, it's okay. Just one item. It's 2.96 multiplied by 10 power minus 19.
19
Yeah.
with the square root
Yes.
and the d cubed.
Yes.
Okay. Now we'll square both sides. That's why I didn't want you to take the root. So here you have 3.1 times 10 to the 7 squared divided by 2.96 times 10 to the minus 19. That will equal d cubed. So please now calculate what I have on the left here.
I get 2.97. What is
Did you write 30? It's not 3, it's 30.
Ah, 3.
Yeah, you wrote 30. Still, maybe you should write 30.
Yeah, no.
Where?
It's on the, there you go. No.
Sorry.
The mass of the sun.
Mass of the sun is.
Oh, sorry, I wrote 3.
Yeah.
30. Thank you. So I'm wanting you to calculate this, please.
I found 1.76 multiplied by 10 power 24.
1.76 multiply,
By 10 power 24.
that equals d cubed. So now get the cube root of this number.
Oh, God damn. I got it wrong, sorry.
Alright.
I get 4.
Wait. We'll go with Jing Dong. What did, no, just read it out. What you got, Jing Dong?
What?
What did you get? No, tell me.
4.783950617.
Alright, Jing Dong, start that again. 4.7.
83.
Okay, blah, blah, blah. Times 10,
32.
32.
32. Yeah.
That equals d cubed.
Yeah.
So d equals cube root this, please. Cube root.
10 power what?
32.
32.
Oh, it's 7.81. 82.
Times
10 power 10.
10 power 10.
Yeah.
Fine, okay. I'll just assume nobody made a calculation mistake with this question. So that is the average distance between the sun and the earth. Sometimes it is more, sometimes it is less. That's the average distance. Is it the same answer, Albert, or did you get?
3.25 times 10 to the power of 33.
In this step here,
Yeah.
you got a little different.
Yeah.
It doesn't matter now.
It doesn't matter.
Oh.
Well,
It means that just follow the same step.
but yes, but the same steps. I really need to get a calculator so I can do this at the same time too. Okay, so anyways, the most important thing was showing you how to use the formula. Yeah.
Can you go up?
Yes. Well, you mean the last page?
Yes, go up, go please. Go up, please.
Up?
Yes. Okay, why should there need a...
Oh yeah, if you look here, the formula is for t squared.
yeah.
So all I did was cancel this
Oh yeah, I know.
and put it there, if you like.
Oh, yeah.
Is that okay, Ted?
Yes.
Xingdong did something interesting today. Yeah, I wrote an example on the board and he didn't write it down. Yeah?
Just like you.
Remember?
No, I write it down.
Yeah, now you do, yeah.
Now?
Yeah, but this is Xingdong's first class. And I did an example and he didn't write it down. Ted knows better than this. Yes. Where is August?
He's waiting for his bed.
For his what?
Bed.
His bed, receive his bed. Sleeping bed.
Sleeping bag.
Yes,
Bed.
he have no bed to sleep, so he bought a bed.
Yeah.
He has no bed to sleep.
Yes.
Is he homeless?
Yeah, is he homeless? What happened to him?
I don't know.
He rent a new house, so he waiting for.
Yes.
So where's he going to sleep?
On the floor?
Later chair.
Aren't you worried about him?
It's a private question.
Alright, fine. Fine, it's private. Okay. Right, just to finish.
Sofa.
Sofa!
Fine,
Sofa! Right, okay. Sofa is fine. Sofa is good. Alright, so just to finish, there's some units I want to show you now. So here is the Earth, and here is the Sun, and this distance here. You see this distance here?
Okay.
That is called 1 AU. And it's the distance that you know, like space is very big.
Yeah.
Mm.
So you can't really use meters all the time.
What is AU?
So AU stands for astronomical unit. Yeah. So AU is astronomical unit. Basically, it's a big
For
unit
the space.
for space. And I'll tell you what it is. It's approximately 149,597,870,700 meters.
Oh.
Yeah, so it's very big. Very big. So if you were measuring distance between, let's say, you and maybe
The Earth.
some other stars, you could maybe use AU. It's a bigger unit.
Wouldn't be enough.
Oh, you know, it wouldn't be, but it'd be better than meters.
What about kilometers?
It's just.
Kilometers? No, kilometers would be way too small. Like, I mean, if you look at this, this is 149
Billion.
trillion, I think.
Billion.
Billion, yeah. 149 billion meters. Okay. And there's another unit, which I wrote down here. And it's called 1 sidereal year. And it equals 31558,149.8 seconds. What do you think this represents?
Is this is being used for velocity?
No, the 1 year is 365 multiplied 24 multiplied 60 multiplied 60,
Yeah.
isn't it?
It's very close to that, yeah. It's basically, remember Albert, we were discussing earlier how 1 year is not really 365 days. So this here is what is the exact, more accurate,
The more exact.
more exact value. This is how many seconds if you wanted.
Using the seconds, we will get 365.24.
Yeah, give me your calculator, let's see what we get. Okay, so if I use this, 31558,149.8 divided by this is minutes now. This is hours. Oh wait, I did something wrong here. Let me type this. 31558,149.8 seconds. So if I divide by 60, I have minutes. Right?
Yeah.
If I divide by 24,
No, not yet.
Hour.
You have to go to hours.
Days. Divided by
You
24 days.
2 times 60, then
What's this,
24.
Mr. Steven? I have a silly question.
well, 1 second once I try and get this on my calculator. Right, that's how many seconds. If I divide by 60, that's how many minutes.
Uh-huh.
Now, what do I do next? Divide by 24.
And mean many days.
How many hours in a day?
How many days?
How many days I have?
No.
We're getting all confused.
Can I see your iPad?
No,
please?
how many hours in a day? When you multiply by 365, how many days in a year?
Right, well, let me just put it to you like this. Hang on. 31558,149.8. Okay. So, if you take, listen, if you take 1 year, so if I do 1 year, go down. If I do 365, multiply by 24, multiply by 60, multiply by 60, it will be smaller than this one.
Yeah.
And how much smaller? It will be 22149.8 seconds smaller.
Is it?
If I subtracted correctly.
Yeah, give it to me. Can you give it to me?
So I think this will be, I think maybe 6 hours, is it? 60. So
Well, it must be
60 times 60 times. Yeah, about 6. Yeah. So this here is about 6 hours. So in other words, 1 sidereal year is approximately 365.25 days. So in other words, this here is more accurate for 1 full year. So this is what you want to use for precisely one year. Okay? This 365 that we use, that's only approximately. Is that okay, Ted?
Yes.
Okay. So you have 2 new units. This unit, wait, give me red. And this unit. Okay. So for this class, you have Kepler's 3 laws. Kepler's 3 laws and 2 new units for today. Okay?
Okay.
Happy?
Happy.
Very happy?
Yeah.
Oh, good. Okay, I'll give you the worksheet on Kepler now. Okay. Oh, let me stop this.
Stephen?